Hello, I'm Nito Cobain. Welcome to Side by Side. My guest today is Dr. Tony Atala, Director of the Wake Forest Institute for Regenerative Medicine.
Funding for Side by Side with Nito Cobain is made possible by...
Here's to those that rise and shine, to friendly faces doing more than their part, and to those who still enjoy the little things. You make it feel like home. Ashley Home Store. This is home.
The Bud Group is a company of everyday leaders making a difference by providing facility solutions through customized janitorial, landscape, and maintenance services.
Coca-Cola Consolidated is honored to make and serve 300 brands and flavors locally. Thanks to our teammates. We are Coca-Cola Consolidated, your local bottler.
Dr. Atala, welcome to Side by Side. I have been looking forward to seeing you and to ask you, what in the world is regenerative medicine?
Thank you, Nito. It's really nice to be with you today. And regenerative medicine is basically a science. It's a catch term for many different things. It includes basically cells and stem cells and tissues and organs that we create in the laboratory or manufacture for patients so we can basically improve and heal their tissues and organs.
So what does that mean? Does that mean that we're going to live to be 120? Will you make that promise on this program here today?
Absolutely not.
No such commitment on your part.
No.
So, but what is the intent of it? Is it to make us live longer, to make us live healthier? What is the purpose?
You know, we basically, as you know, as we age, our organs tend to start to fail. And that's natural, you know, and that's why right now the number of patients on the transplant list has really tripled over the last several decades. And that really has to do with the fact that we're living longer. And as we live longer, our organs basically start to fail. So the question is, how can we help that process to regenerate those organs, if you will, and give you a better quality of life?
Are you suggesting that there will be a day when we no longer need organ donors, for example?
Well, certainly that's the long-term goal, is to be able to create these tissues and organs in the laboratory so that they're available when the patient needs it.
So walk us into the laboratory. Will you please explain to me, a novice understanding what you are talking about, how it goes from A to Z. What is it? Where do you get the content that you need? How does it work? How do you place it back in my body? What are the challenges or the obstacles inherent in such a process?
So the process is a patient who's identified with a diseased or injured organ gets a very small piece of tissue taken from their organ, basically about the size of half a postage stamp. We then take that tissue and we tease the cells apart from that same patient, isolating the normal cells. We expand the normal cells. We then use various methods to create the tissue and the organ that we can then put right back into the patient.
Literally, that's what you do. You take a small piece of that organ and then you place it back in the body of the human being.
Yes, by doing it in that manner, we avoid rejection. Because right now, if you need an organ for transplantation, for example, you have to go to a donor, either a life-related donor or someone who just passed away. And that organ does not belong to that patient. So that patient's natural reaction is to reject the organ. And that's why these patients have to be on medications to prevent the rejection. So that the strategies will use the patient's own cells. Therefore, we create the tissue and the organ, and the body recognizes it as their own.
And so where are we in this process? Are we, I assume we're not in the stage where you're actually doing that every day with human beings. You're still in the research stage. You are, how far along? Can you give us some indicator when we can do this successfully and continually?
So basically, we have done this in patients now with a number of organs. And the strategies, as I mentioned, you know, you take this small piece of tissue, we expand the cells, and we create a three-dimensional mold that basically replicates the structure of the organ. So we then can make that by hand, or we can print it, and we can then allow it to mature and put it back in. And we've done this now for a number of different tissues in patients.
Give us an example. What would be one of those organs that you've done that with?
So starting from the least complex, and we go from least complex to most complex. In the body, we have many different tissues and organs, of course. And the least complex are the flat structures, such as skin. Now, they're all complex. They're all very complex, but structurally, the flat tissues are the least complex, like skin. And we've done that with skin. Tubular structures are the next level of complexity, like blood vessels. Like urethras, we've done urethras in patients. Hollow non-tubular organs are the next level of complexity, like bladders, for example. And then the most complex organs are the solid organs, like the heart, the lung, the liver, which are much more complex and still with time to come.
What about success rate, Tony? You're optimistic, obviously, about the future. You're thoughtful about the present. Where are we in terms of your prediction of success? At what point might we say this has become sort of the norm in healthcare?
Well, you know, we're going through the clinical trials, of course, in terms of technologies.
And how long does that take typically?
You know, that typically takes about 15, 18 years to get the product out. It really does. You know, even for a pill that you take, you know, like a blood pressure pill, the timeline, the average timeline is about 15 years.
I've often wondered why. Why 15? Why not 30? Why not 5?
You know, it takes time from the time that you place that first therapy into the first group of patients to actually assess and make sure the technology is going well. Then you have to do a second phase trial by the FDA, which regulates these trials, the Food and Drug Administration. And then finally a third level of trials before it gets finally released. And each stage takes, you know, a number of years at a very high cost, actually.
Yes. So my original question about prediction of when we might get to a stage that you feel very persuasively confident that we're going to be successful, what are we looking at really?
Well, some of the less complex tissues are already making their way into that process, like skin, for example. So, you know, we will see the way that these tissues will be out into the general population, not just in clinical trials, because they are available now in clinical trials for patients in limited numbers for specific tissues. But right now, the ones that are least complex will be the first out the gate for the whole general population.
When you say skin, you're talking about dermatology, for example? You're talking about, you know, Mohs surgery? What are you talking about when we say skin? Are we talking about accidents or burn or?
Yeah, the number one area is burns, actually, where it's needed the most. You know, because burns really can take a toll on the skin, of course, the first protective barrier. But also patients with injuries, trauma, you know, chronic disease of the skin. So anything where skin replacement is needed.
And you said it costs a lot. Obviously, it costs a lot. Where are you getting all that money from, Tony, to make all of this? I assume you have a lot of people on staff. Is that right?
Yes.
Give us an idea. How many MDs, how many clinicians, how many assistants?
We're very fortunate that at the Wake Forest Institute for Regenerative Medicine, we have over 400 people working together, really to bring these technologies all the way from the bench to the bedside. And it really does take a village, you know, so we have molecular biologists, cell biologists, material scientists, biochemists, physiologists, physicians, all working together to bring these technologies all the way through from the concept to the actual application to the patient.
And is the funding coming from, I don't know, pharmaceutical companies, or is it coming from government grants, or is it coming from individual donors? I assume there's takes a lot of money to pay 400 experts in the field.
You know, we're very fortunate that the federal government has really made this a priority in many areas. So we have funding from many different sources: the National Institutes of Health, the Department of Defense. For example, one of the major programs we've had for a number of years is the Armed Forces Institute for Regenerative Medicine, which is a program we run out of Wake Forest with a collaboration with 30 universities nationwide, where we can deliver these products to patients and our wounded warriors. So there are many different sources of funding, and thankfully that is something that allows us to keep pushing these technologies which are so badly needed.
And Tony, this is all amazing. You know, to the average lay person who doesn't understand the technical and mechanical aspects of which you speak, it's amazing to me. I know that you are the creator of the 3D bioprinter. What in the world is that? I know what a 3D printer is, but a bioprinter is what?
Well, we help to accelerate the technology for this particular purpose. And so a 3D printer is really nothing more than the printer you see at home, you know, with your desktop inkjet printer. And that's really how, in fact, we got started. We started out by using just your typical desktop inkjet printer. We realized that we needed to scale up the technology manufacturing process, because what we had done with our first number of tissues, we were making these by hand, one at a time. And obviously, we needed to scale up these technologies to the point where you can make them in large quantities. So there's nothing magical about the printer, really. It's just a machine that automates the process of manufacturing. But what it does do is it gives you reproducibility, it gives you scalability, and you're able to reduce the cost of the production. And all good things when we finally get these technologies to patients.
Do you see a time when we might have, I'll use the term, mass manufacturing of all of these needs for regenerative medicine?
You know, manufacturing is interesting because this has been identified as a major challenge by the government in terms of keeping manufacturing here in the U.S., because we're very good at innovation,
yes,
but we're not necessarily very good at producing the product, and we've seen that with many industries.
Why is that, Tony? Why aren't we going to be? We're a leading nation in the world. Why aren't we as good as we ought to be in that area?
You know, we are good at innovating the science, but when it comes to manufacturing, those end up going abroad. And
yes,
you've seen that with the computer business,
yes,
you've seen that with the battery business. And the reason for that is that when you're innovating the science, you're not necessarily innovating the manufacturing process. So you have to do both in tandem so that you're not just doing manual labor, you're using automated products. And that's really one of our major areas of, one of the major areas we're focusing right now is making sure that we can innovate in manufacturing as well.
So I read somewhere something about the NASA Vascular Challenge. What is it? Tell us what that is and what was your role in it?
Interesting, you know, NASA, along with the Methuselah Foundation, they put out a challenge, and they have these centennial challenges that they do all the time. And the challenge was to basically create vascularized solid tissue, or solid tissue that has the blood vessel feed necessary for the tissues to survive, which is a major challenge for solid organs. And so we were able to look at this challenge when it came out a number of years ago, and we decided to go for it. And so we had two approaches to the challenge in terms of manufacturing solid tissue. And using our printing strategies, we came up with two different strategies, and we had team members, the same team members, looking at both approaches. It was basically the first to reach. And luckily, both approaches worked. So both approaches that we proposed to NASA worked, and that is leading to more work with NASA, including, of course, getting these up into the space station and making sure that we can follow these long term.
Congratulations, that's wonderful. You are the one who developed the first lab-grown organ. I'm imagining in my head this organ, part of my body that you developed in a lab. Will you take us there and explain it to us average people? What does that mean?
Yeah, certainly we implanted the first organ in a patient, inside a patient, and that was really...
It was a lab-grown organ.
It was a lab-grown organ.
What does that mean, lab-grown organ? Artificial organ?
It's actually an organ created with your very own cells.
I see.
So, you know, there had been a lot of work done in the area of trying to create tissues. And the challenge with creating tissues outside the body is that we couldn't even get the cells to grow. I mean, for most tissues in the human body, just 30 years ago, we did not have the technology available to get normal human cells to grow and expand outside the body. And so a lot of advances now, right? I mean, amazing where we are today, because most human cell types can now be grown just a few decades later. The other challenge was using the right materials, So when you grow the cells, they're just cells. But how do those cells reassemble themselves to create tissues? And so that, that was another area of study that many people were involved in, and we were able to basically create these cells and scaffolds, put them together, and basically implant an organ inside the body.
Dr. Atala, all these changes and developments and the transformative ideas and creativity vis-a-vis regenerative medicine and more, what is going to be demanded of our healthcare system? I think hospitals, I think medical schools. What needs to happen to accommodate all that? You speak of these clinical studies that take 10, 15, 20 years, et cetera. We're going to come to a point where all of this is somehow, arriving to a point of mastery, and it's going to demand some support system. Are we going to completely change the way the healthcare system works? Take us on that journey of acknowledging what that really means to us. Is it more equipment? Is it teaching people in medical schools completely differently? Is it preparing the mindset of the patient in a completely different zone, et cetera?
Certainly our mission is really to improve patients' lives through regenerative medicine. That's our mission. And the way that we accomplish that is really by making sure that we can improve lives so that people are not in pain, they're not in end-stage failure, that we can actually heal in a better way, so that we can actually hopefully cure some diseases instead of just managing them, which is really a very long-term goal. But the fact is that if you're a patient who has kidney failure, let's take that one example, a patient with kidney failure, they're going to be going to dialysis, which is hooked up to a machine, where they're going to be hooked up to this machine 3 times a week, and they're going to be spending 3 days a week on this machine. The average cost to maintain a patient on dialysis is about $250,000 per year.
Really?
Really.
How do people pay for that?
The healthcare system is paying for it, and so all our insurance premiums, the government, all this goes to pay for that patient. So. And not only that, that patient is no longer a member of society who can actually go out and have a regular full-time job, right? They're hooked to this machine 3 times per week. So really, the cost of these technologies are high, but at the end of the day, they're much lower than having a patient's alternative like dialysis. So that is where we really push to make sure we make these technologies available to as many patients as possible, and that we keep the cost down.
But hospitals have to have different equipment. Doctors have to have training in these areas, right? Are we in parallel in America today, research matching preparation of professionals to deal with the outcome of this research?
So, with these therapies, which include cell therapies, by the way, that we haven't talked about much, but any of these therapies, at the end of the day, the physician's going to deliver the therapy in the way they usually do, right? So, for example, the surgeon is going to replace an organ. Instead of using a prosthesis or a donor organ, they're just going to use this organ. But someone needs to manufacture it, and of course, these are the manufacturing areas and centers that need to be built with industry support and government support to make sure that we can provide these to patients.
I see. Well, that's encouraging, what you're saying. It's encouraging that we don't have to change the whole ecosystem to make it work. You speak of cell therapy. What is that?
So cell therapy is basically a strategy where you're not creating a tissue or an organ, but you're actually using the cells themselves to provide the healing process or the treatment.
And give us an example of...
An example of that, for example, is a patient who does have kidney failure, getting back to the same example. Right now there's some clinical trials ongoing where you can take a very small piece of tissue from that kidney, less than half the size of a postage stamp, isolate the normal cells, and then take those cells and mix them with a gel and put them right back into the patient to augment their function. And so using the cells, but we're using tissue-specific cells, because those tissue-specific cells from a kidney to a kidney from a liver back to a liver. Those cells know what to do, and they're going to stay in that organ, and they're going to create new tissue and do what they're supposed to do, hopefully.
Tell me what worries you. You are so invested in this. You're editing 3 scientific journals. You've written about 25 books on the subject. You are known nationally and beyond as an expert in the field. You have brought a tremendous amount of substantive and substantial knowledge and data to this area. Surely you worry about some things. What are they?
Well, you know, interestingly, the first thing I need to tell you, of course, is teamwork, right? We couldn't do what we do without teamwork. And having all these people working together to advance these technologies. And the worry is always to make sure that the technologies really do help the patient and they don't hurt them. And so that's the challenge, right? Every time that we're about to bring a tissue or a technology to a patient, once we make that decision, we've tested that technology every single way you can think of, right? We've tested at the bench, we've tested preclinically many, many different times, and we finally get our team together and we say, okay, is anyone here who is not willing to put this technology in your own loved one?
Great question.
Right? Are you willing to put this in your own child?
Yes.
In your own parent?
Yes.
Unless everyone agrees, we won't do it.
I see.
And even when we do transfer the technology to patients, it's like anything else. You have to make sure that the technology is going to be safe. And our number one directive, right, that as physicians, we take this oath, primum nocere, which is first do no harm. And the patients who enter the clinical trials are real heroes because they're really going out there and they want these technologies, but we want to make sure that we temper that with the reality that these are, in fact, clinical trials.
Well, I hope you know we all appreciate you because we are all concerned about our health, our future, our families, our well-being, and it takes masters like you who dedicate their life to helping us all in this way. I want to talk about you for a minute. At what point in your life did you become interested in science?
Well, that's a very good question because, in fact, of course, I liked science, but I never saw it as part of my career or my future. Never. In fact, along my whole training, I just wanted to be a clinician, just go and treat patients. And it was interesting because at the very last level of my training, the program that I was training at, the head of the program, who was a surgeon-in-chief at Children's Hospital and Harvard Medical School, Dr. Alan Reddick, said to me, you know, I'm going to give you an opportunity to add a year of research to your training. And I basically told him, I said, I really don't want to do that. I'm just interested in clinical practice. I don't want to do research. So he said, really? And I said, yes. He said, you know, I really think you ought to do it, so why don't you give it some thought? And I'm going to call you in a week or so. I said, okay. So he went ahead and gave me that week to think about it. I talked to my friends, I talked to my mentors, I talked to my wife, and he called me back a week later and said, well, are you going to do just the clinical track or the clinical track plus the research? And I said, you know, Dr. Reddick, I've given it a lot of thought, and you're so nice to bring this up, but I still don't want to do it. And he said, really? I said, yeah. I said, well, okay, is your wife home? He said, yes. Can I say hi to her? I said, yes. Spoke to my wife. My wife got off the phone 2 minutes later. She looked at me and said, you really got to do that research here.
And you did.
And I did, and that's
And
how.
that's the end of that. And we're all the beneficiaries because of it, Dr. Tony Atala. We're grateful to you that you have a wife with such wisdom who directed you in the right way. Look, Tony, I've known you for a long time. You are an extraordinary human being whose service to humankind is amply observed by so many and appreciated by one and all. I know that you've traveled across America and the world lecturing on these subjects and building bridges of understanding with other people about these rather complex subjects for those of us who are not engaged every day in it or who have the comprehension or understanding to be involved in it. But just know that your work is significant for all of humanity, not only in the United States, but across the world. And I, for one, am very grateful to you for all of that. And I look forward to your next big project. What is it? Shortly, in a few words, is it a book? Is it a lecture? What is it?
You know, our project really is to keep building the regenerative medicine infrastructure, what we call the Regenerative Medicine Hub, which is really bringing all these different stakeholders together. Basically, workforce development, we're developing this national workforce for the field, incubators, a test bed where companies and individuals can test their technologies at a low cost. So really bringing this infrastructure for the field in the future.
I have a feeling you will do it. Thank you for being with us today on Side by Side, and thank you for joining us on this important program, and I'll see you on Side by Side again next week.
Funding for Side by Side with Nido Cobain is made possible by
Here's to those that rise and shine, to friendly faces doing more than their part, and to those who still enjoy the little things. You make it feel like home. Ashley Home Store. This is home.
The Bud Group is a company of everyday leaders making a difference by providing facility solutions through customized janitorial, landscape, and maintenance services.
Coca-Cola Consolidated is honored to make and serve 300 brands and flavors locally. Thanks to our teammates. We are Coca-Cola Consolidated, your local bottler.